All right, everybody, welcome back. So before I start the lecture, I want to oop. I want to say a couple of things about what's coming up. Okay, so Wednesday. We'll have our usual meeting at 16:30. I'll try to keep it short. Okay, and then at 17:30 we'll have a quiz. It'll be available at 17:30 on Leah, the questionnaire. You'll have an hour to complete it, which is way more than enough. Okay, and to upload it in PDF, please. It'll be on double integrals over rectangles only. Okay, so short question on that. It's mostly to keep you up to date as usual for quizzes, but also that you see how it'll go for the test. Okay. Yes. Is that 15.1? What chapter in the book is that? Yeah, it depends on the edition that you have. So this would be 15.1 or 15.1, 15.2, depending on the edition that you have. Is there a class after the quiz? No, of course not. No, so from 5:30 to 6:30, it's the quiz plus uploading, and that's it, right? Okay, so there'll be a short class before, and then after that, it'll be the quiz. Okay. Yeah, so in some of the books, in some of the editions, double integrals over rectangles, I think, are in 15.2. That's probably in older editions. The newer edition, I think it's included in 15.1. You'll just look it up and you'll see, okay? What else do I need to tell you? Yeah, so the test is next week. Okay. Any questions or comments? And there you have a WebWorks also, which is open, which covers exactly the stuff that we've been doing and we'll be doing. So, okay. All right. What sections will be on the exam finally? So it should be chapters 14 and 15, right? So test covers all after the material for test 1. So I'm going to write that here, but I will send you a message which will be more official. Okay, so it's roughly chapter 14. This should be 14.1 to 14.6. We may have skipped something in there, I'm not sure, but I don't think so. And chapter 15, 15.1 to 15.4, or depending on the edition that you have or that you're using. Okay, so when I send you a message, I'll put the topics too, right? But you can look at the course outline and you'll see. And also section 10.3, which is polar coordinates, which is what I'm going to do today. Okay. Okay. So that's just roughly, so it's chapters 14 and 15, basically. Okay. Other questions, comments? All right, so that's for the business arising. So let's see what's left to cover in the course. So what's left? So I'm going to do 10.3 today, polar coordinates, and then 15.4, again, it could be 15.3 depending on the edition, double integrals in polar coordinates. So let me explain a little bit what this is about. Okay, so what's the idea? So if you remember in Cal 2, we saw something which was the substitution rule, right? Which in a sense is like a baby case of what we call a change of coordinates, which is what we want to do here, okay? So for functions of several variables, okay? So similar principle, I mean, similar idea in several variables, but in a sense, it's way more involved because of the regions, right? So more involved. Because in one variable, you're integrating over an interval, basically. So that's it. There's really no. So you might stretch things around with the substitution rule, but it's mostly a technical trick to be able to find antiderivatives. But in several variables, if you're going to integrate over certain regions, it is often just basically too difficult to do it with the normal rectangular coordinates that we're using. So if you change the kind of coordinates that you use to describe the points in the plane, you can transform an integral which is difficult into an integral which is either doable or easy. Okay, so that's the idea in general. So the general idea is change of coordinates to better describe regions. Okay, so that's the general principle, and there's a theorem which is the change of coordinates, which tells you how to change coordinates and how to integrate. And we're going to see a very special case of that in 15.4, which is for the change to polar coordinates. Okay, so let's plunge into polar coordinates. It's actually very natural. Okay, so what it is, it's an alternative way to describe an alternative coordinate system for the plane. Okay, and okay, welcome. Okay, and again, the idea is that for certain regions, describing them in this alternative coordinate system makes them much easier to handle than in a rectangular coordinate system. Okay, so here we go. So here it is. Okay, so rather than having two axes which are perpendicular, we actually have only one half axis, okay, and a base point, okay? So you fix a point O, and this would be the origin, right, usually. Okay, and choose a half line starting at O. And for us, it'll be the positive x-axis. Okay, so I have my point, and I have my line, half line like that. Okay, and I want to describe the points in the plane relative to these two things. So let's take a point P in the plane like that. Okay, so I want to describe, so the polar coordinates of a point P are two numbers, r and theta. What are those? R is the distance from O to P. Right, so R is just the distance O to P. Okay, and theta, as you can probably guess, will be the angle starting from the coordinate line L to the segment OP. Measured as usual in radians. Okay, so you take any point in the plane, and it has two coordinates, r and theta. R is the distance to the point O, and theta is the angle. Okay, so there's obviously slight differences from rectangular coordinates. Rectangular coordinates are unique, right? So if I give you x and y, there's only one point and there's only one xy for that point. It's not the same for polar coordinates. So notice this. Not unique. Obviously, if I add 2 pi to the angle theta, I'm going to get the same point, right? So we can add multiples of 2 pi, integer multiples of theta, right? As usual. So if it's 0 or 2 pi, it's going to give you the same point, right? If you look at the point O itself, it has infinitely many pairs that represent it, right? So that's the first thing. So O has coordinates, again, polar coordinates, 0, theta for any value of theta, right? So obviously if R is 0, then it's got to be the point O. The angle could be anything. That's always the point O. Okay, you're the origin. Okay. Now, there's a really cute convention that we're going to use where we're going to allow R to be negative. And it's very natural. Okay, it's very useful. And so here's how this goes. Okay. I'm gonna Okay, so here's a convention. So we allow negative R as follows. So I'm just going to show you an example and you'll see exactly what I mean, then I'll write down what it means, okay? So suppose for instance, that I take the polar coordinates -1 pi over 4. So what is this point? Well, okay, so I look at the angle pi over 4. So again, this is my origin and this is my line here, but I drew the usual rectangular coordinates axes. Okay, so this is pi over 4. If it were +1, then I'd have the point over here, right? But it's -1, what do? You go in the other direction, right? So it makes a lot of sense, right? It will be right here, right? So -r, you go in the other direction. Okay, hopefully that makes sense. Okay, so formally what it means, so if r is negative, then r theta same as minus r theta plus pi. Again, notice this is positive, right? Okay, so you add pi to your angle, so you're going in the other direction, and you go that distance, absolute value of that value of r, right? Okay, so let's do a few examples, okay? Let's see what this is about. Okay, so plot the points with polar coordinates. Um, 1, 5 pi over 4, 2, 3 pi, and minus 3, 3 pi over 4. Okay, so let's do that. Okay. So 5 pi over 4, that's 1, 2, 3, 4, 5. And length 1, so that's my point. Let's call this P, Q, R, so this is P. Or this length here is 1. Okay, so find the angle and move in the direction of the angle for that length R. Okay, so that's P. Let's see, Q, so 3 pi, so that's 1 pi, 2 pi, so 1 pi, 2 pi, 3 pi, right? And length 2. So that's Q right there. Okay, and finally R. Okay, so I look at the angle, 3 pi over 4, so that's 1, 2, 3. Okay, but now R is minus 3, so I'm going in the opposite direction. So 1, 2, 3, like that. Hopefully that makes sense. Okay, so it's pretty straightforward. It's just a different way of, and I don't know, maybe you've seen this in physics, maybe it's used, I don't know. And especially not this semester. Okay. All right. So now what we'd like to do, so we understand how this describes the points in the plane, how do we go from one set of coordinates to another? Okay, this is really important. So how do I convert polar to Cartesian and Cartesian to polar? So let's take a look at that. So I might say also rectangular coordinates. I mean the same as the Cartesian coordinates. Okay, so let's start. Suppose P has polar coordinates r theta, right? What are its rectangular coordinates? Cartesian. Well, if you think about it, right? This is a length r. This is an angle theta, right? So you're on the circle of radius r at angle theta. So what are the coordinates? R cos theta, R sine theta, right? Now in my picture, I cheated because obviously I used the positive r. So you're going to say, well, what happens for negative r? Magic, it still works, okay? I can let you work it out, but it's basically just if you think about what happens to cos of theta plus pi and sine of theta plus pi, you'll see that it works out. The minus sign will come out. Okay, so works also if r is negative. Okay, so it works in all possible cases. Okay, so check it out. Okay, so it's just simple high school trick. Okay. Okay, so that's if you have the polar coordinates, you can find the Cartesian coordinates. The other way around is just slightly trickier. Okay, so if P has Cartesian coordinates xy, what are its polar coordinates? Well, you can't really write it down in a simple way. So let me explain. So the first thing is that clearly r squared is x squared plus y squared, right? So if you have your point here, this is x and this is y, right? What is this distance given by Pythagoras, right? R squared is x squared plus y squared. So r will be, if you take the positive value, the square root of x squared plus y squared. That's fine, okay? What about theta? How do you find this angle? Well, here's a trick. I don't know if I've talked about it in class before, but it's something I always tell my Cal 1 and Cal 2 students, that somehow a lot of people don't think about, but what is the tangent of an angle, right? It's the slope of the line, right? So it's y over x. So the other thing that you want to keep in mind is that tangent of theta is y over x. Now, obviously, x cannot be 0, right? If x is 0, then you can figure out the angle. It means it's either, let's say, minus pi over 2 or pi over 2. But the problem with what I wrote is that it doesn't give you the unique values of r and theta. There are actually 4 possibilities, and 2 of them are no good. Okay, so warning. This gives 4 possibilities, but 2 of which are not good. And I'm going to show you an example. So must check the quadrant. Okay, so you won't have to be honest, I'm telling you right now, but you won't really have to deal with that very much. Okay, when we do integration, it's not going to be a problem. But I need to tell you just in case. Okay, so here is an example. Okay, to illustrate this. Okay, so first let's convert 2 pi over 3 from polar to Cartesian. Okay, so these are the polar coordinates of the point, and so I know, so this is r, this is theta, so I know that xy is given by r cos theta, r sine theta. So this will be 2 cos of pi over 3, if I have to think about it. So pi over 3 is the big guy, so cos is 1/2. And sine is root 3 over 2, right? So the Cartesian coordinates are 1 root 3. Okay, so that's straightforward. So polar to Cartesian is just straightforward. There's no problem. Okay. Now let's go the other way around. Let's convert, sorry about that. 1 minus 1 from Cartesian to polar. Okay, so I have my x and my y. I need to find r and theta. Okay, so let's just write down what we had. We had that r squared is x squared plus y squared. So this is 1 squared plus minus 1 squared, which is 2. Okay, and we know that the tangent of theta will be y over x, which in this case will be minus 1 over 1, which is minus 1. Okay, this is the slope of the line through the origin through your point. Okay, so it means that the angle theta is either 3 pi over 4 or minus pi over 4. It's one or the other. Okay, so this gives theta equals to 3 pi over 4 or minus pi over 4. Okay, and this gives r equals either root 2 or minus root 2. Now, you see that gives you 4 possibilities, okay? And you have to figure out which one it is. Now, here you have to look at the quadrant, okay? So check quadrant. So the point 1 minus 1 is over here, right? So it means that, let's say I have to go here. So it means that the angle, you can either choose, so the polar coordinates are either, so you use minus pi over 4 as your angle and the positive value for r, or you can use the angle on the other side and the negative value for r. So minus root 2, 3 pi over 4. Okay, the other two possibilities are no good. Right, you see that this would give the point on the other side. Is that okay? Hopefully. Maybe, maybe not. Oh, got a chat. Makes sense. Very good. Excellent. Okay. Okay, so we've got our polar coordinates. We know how to go from one to the other. So now let's see why we need this or how we can use them. So what I want to do now is to sketch curves which are given by polar equations, right? So now I have a description of the points in the plane, I can write down an equation involving, let's say, r and theta. This will define a set of points in polar coordinates. What do I get? Okay, so we would like to look at some basic examples of polar curves, and then by extension to polar regions. Polar regions, interesting. But anyway, okay, so curves and regions in polar coordinates. Okay, so let's start with some really easy ones, okay? So let's start with the set of all points r theta, this is in polar coordinates, such that r equals to 2. What is this? Okay, so what does it mean? So you look at all the points. What is r is the distance to the origin, right? So it means this is the set of all points whose distance to the origin is 2. Pretty simple, right? So this is obvious. This is the circle of radius 2, centered at the origin, right? That's exactly what it is. Okay. Now notice, and I'll repeat this as we go along, how simple the equation. It's a linear equation, right? In polar coordinates, a circle has a linear description, which is not the case in Cartesian. You need a quadratic to describe a circle, right? So maybe it's giving you a little hint at where this is going, right? Okay, so you see how to describe any circle centered at the origin, right? Super easy, r equals to whatever value you want, right? Okay. Okay, here's another one, similar. The set of all r theta such that r is between 0 and 2. So I'm looking at all points with polar coordinates such that r is between 0 and 2. So that means the distance to the origin is any value between 0 and 2. So what is that? Disk of radius 2, right? Right? Yeah, let's make use of a technology. Okay? Be careful. If I write instead of the set of all points where r is between 0 and 2, if I write this instead, suppose I write that, what happens? I need an answer, quick. What points can I get if I make this?
Would it be the same?
Nope. Hint. What happens if r is negative?
It would be the whole plane.
Correct. Yes. Because now you're allowing r to be any value which is negative, right? And by our convention, you can describe any point with a negative r. The angle can be anything. So this is the whole plane. Right? So if you take any point anywhere, right, look at its distance, let's say it's 100, right? but then its polar coordinates can be written as minus 100 theta plus, if this is theta, right, then P has polar coordinates minus 100 theta plus pi also, right? So then R is less or equal to 2. But all of this is in 2D only. Yes, absolutely. This is in the plane. There are equivalents in 3 dimensions of polar coordinates. There are actually various. There's spherical coordinates, cylindrical coordinates. We will not go there because we're not doing triple integrals. So what we want are descriptions of regions in the plane over which we will integrate. Okay, so that's why it's only in 2D. If we had a normal semester, I'd be going to triple integrals, and then I'd introduce spherical and cylindrical coordinates in 3D. Okay, this is only 2D. All right. Okay, how about another example? The set of all r theta such that theta equals to pi over 4. Was ist das?
Is it a line?
Yes. And it's not a half line, it's actually the full line because of that convention that we allow r to be negative. So this is the line through the origin at angle pi over 4. So you take pi over 4 like that, and it's the full line. Why? Because of our convention. So these points have r negative, right? So r equals to 0 is here. As r grows positive, bigger and bigger, you get this way. R negative, you're going to get the other direction. So yes, that's the line through the origin at that given angle. So we can nicely describe all the lines through the origin. Describing a line not through the origin is a completely different matter. In polar coordinates, that's not ideal, okay? All right, let's look at some other examples. Here's this example is like simple, but it contains the whole idea of why we're interested in these coordinates. Let's see. So sketch the region, the set of all r theta such that r is between 1 and 2, and theta is between 0 and pi over 4. Okay, so again, we interpret this. So r is between 1 and 2. So these are points whose distance from the origin is between 1 and 2. If there's no restriction on the angle, right? So if there were no restriction on the angle, we'd be getting all the points here, right? That would be r between 1 and 2. But I'm restricting the angle to be between 0 and pi over 4. So now what do I get? I get this piece only, right? This is it. This is it. Hopefully that makes sense, right? I think this is pretty straightforward. But notice, look at this region, and is that a type 1 region in our, recall from the last class, is that a type 1 region? Sort of, but really ugly. Is it type 2? Sort of, but really ugly. But look at its description in polar. What is it? So if you're a person who lives in the polar world, what is that? It's a rectangle, right? R is between two constants, theta is between two constants. It's a rectangle. So if you live in the polar universe, that's as simple as it gets. It's a rectangle. So notice this is a polar rectangle. Right? The description is exactly the kind of thing that we're happy to get when we're doing a double integral. Now, the only question that remains, of course, is, well, if I'm changing the coordinates, what happens to the integral? We'll see that next class, okay? And it's not too difficult, okay? So I think this motivates a little bit the kind of thing that the reason why we're doing this, okay? All right, so now I have two more examples, which are a little bit more involved. And I'm going to show you a little bit how you can approach understanding these curves in polar coordinates. They're a bit more involved. Okay, so let's see the following: sketch and identify curve with polar equation R equals 2 cos theta. So in other words, what I'm looking at, I want to know what is the set of points with polar coordinates R theta such that R is equal to 2 cos theta. Okay. So we're not used to this. So of course, what you could do, and we will do it in just a few minutes, is to convert this to Cartesian coordinates. It turns out that this curve is something that you know, and it has a pretty decent Cartesian equation. But this is not always the case. The next example that I will do, if you try to do that, it's not going to help you at all. You're going to get a nasty looking equation of degree 4, and it's not going to do anything, right? So what I'd like to do is to analyze this curve in polar coordinates. Okay, so we analyze the curve R equals to 2 cos theta to get a rough sketch. So how am I going to do this? What I'm going to do is basically look at the possible values of theta. You see R is a function of theta. So I'm going to go through the possible values of theta and look at what happens to R. Okay, so we look at values of theta going from 0 to 2 pi and see what we get for R. Okay? The key point, or one of the key points, is R can become negative. Obviously, if you look at cos theta, it's going to be positive some places and negative somewhere else. So the key points is where does it change signs, because it's going to change the description of the point in the plane, right? So look for sign changes in R, okay? So that's a little technical trick. Okay, so here is where I'm going to sketch my curve, okay? And here I'm going to look at values of theta and R, which is 2 cos theta. Okay, so here's what I'm going to do. So the cosine, of course, at 0, it has value 1, and as theta increases to pi over 2, the cosine decreases down to 0, right? So here, let's say theta goes from 0 to pi over 2. So in my picture, I'll change the color. So I'm looking at angles going like that, right? What happens then to 2 cos theta, it starts at 2, and it decreases down to 0. That's what happens to the cosine, right? So what does that mean? So it means at 0, I have a point here, right? At angle 0, r is 2. And as the angle starts to change from 0 to pi over 2, the value of r decreases down to 0. So the way I visualize this is, imagine, I don't know if you can see this. Yeah, this way. So you have a segment that's moving from 0 to pi over 2, and you have a point that's moving along this segment at the same time, right? So at the start, it should be here. The origin is here. I'm doing this in a mirror. It's really weird. So this is at 2. And then the point starts to get closer and closer to the origin as you go like that, right? I don't know if you see what the point is doing. That's kind of cool. Let's do this for 10 minutes. Okay, so as the angle is changing, this thing is going to get closer and closer to the origin like that. Hopefully you see what's going on, right? So the curve is going to go something like this. I just want a rough sketch, right? So as the angle goes from 0 to pi over 2, the value of r, which is the distance of the point to the origin, is decreasing from 2 down to 0. Okay? If you don't see this, just really let me know now, because everything that's going to happen after is basically the same thing. Isn't this exactly the same as having y equals to 2 cos x nu? Because my points are plotted as polar, right? R theta. When I'm plotting a point in the plane, r is the distance to the origin. And if this were x and y, x would be the horizontal coordinate and y would be the vertical coordinate. But here r and theta are an angle and a distance to the origin at that angle. You see? Yeah, good. Okay. All right, so I've reached angle pi over 2. And now I want to look at the angles going from pi over 2 to pi. Oops. Okay, but now something tricky happens, right? What happens to the cosine of angles between, well, let's draw a trig circle. From angle here to here, what happens to the cosine? It starts at 0 and it goes down to -1, right? Multiply by 2. So this thing is going to start at 0. It's going to go down to -2. So now r is negative. So what does that mean? You look at your angle, you go the opposite direction, switch the sign of r, right? So now r is negative. So basically I'm going to look at my angles going like this because I'm flipping on the other side. And rather than going from 0 to -2, I'll be going from 0 back up to 2, right? So negative. Okay, so that means opposite side. In other words, plus pi, and flip sign. Okay, so now when I'm plotting the points, when I'm starting at pi over 2, I'm going to go to the other side, but I'm at 0, so I'm still here. And now as my angle goes, sorry, the pi, you flip on the other side, now the r is going to increase back to 2. So basically what you're going to get are points that are getting further and further out until you reach back 2. So we get something like that. That's the trickiest thing. That's if you understand what I just did, you've understood the toughest thing that I'm going to do in these examples. Okay, that's where it is. Okay, is that okay? Okay, so now I've reached theta equals to pi. So I keep on going. Right, so now I go from pi to 3 pi over 2. So what happens to the cosine here? It goes from -1 back up to 0. So multiply by 2. Then 2 cos theta will start at -2 and go back up to 0, but it's still negative, right? So that means that my angles, right? I should be looking at angles over here, but r is negative, so I flip on the other side, right? And I've changed the sign from negative to positive, right? So this is negative. So again, oops, you do that. So you go to the other side, which we've already done, and you're going from 2 down to 0. So basically we're going back over the same piece of curve a second time. Okay, so we go over first part of curve again. Okay, so we're over here, we go back to the origin. Okay, and then the last part, I'll have to erase this, is theta between 3 pi over 2 and 2 pi. What does the cos do? It goes from 0 back up to 1. So in this case, because we're multiplying by 2 now, r will go from 0 back up to 2. So it's positive, so we just sketch the normal way. So the angles are in the last quadrant, and they'll just go over the bottom piece of the curve again. Okay, so repeat bottom piece of curve again. Yes. Is it smooth like a circle, or it doesn't matter? Also, can we have different polar equations that trace exactly the same curve? Yeah, obviously, just like in rectangular, you can write down different equations that will give you the same curve. For the first part of your question, is it smooth like a circle? It doesn't matter. What I'm going to do now, because we were asked to identify the curve, what I'm going to do is to convert it to rectangular and see what it is. Okay, it'll confirm our picture. Okay. Okay, so all right, let's identify the curve. Okay, so I've got r equals 2 cos theta, and our very rough sketch is something like that. So let's identify by converting the Cartesian. Again, I repeat that you can do this for certain curves, but not all, okay? So here's a trick, here are a couple of tricks, right? So what's our way to convert from one to the other? We've got x equals to r cos theta, and we've got y equals r sine theta, and a useful observation also is that r squared is x squared plus y squared, okay? So we're going to use this. Okay, so I'm looking at r equals to 2 cos theta, and I'd like to convert this into x's and y's. Here's like a super standard trick. You see a cosine, right? You know x is r times cosine. So if you multiply both sides by r, maybe good things will happen, okay? So let's see, if I multiply both sides by r, I'm going to get r squared equals to 2r cos theta, right? So okay, now I've got r squared on the left, and I know that's x squared plus y squared. And r cos theta is x, so I'm very happy. I've managed to extract something in rectangular, Cartesian coordinates like that. So now I want to identify this curve. Maybe you're sort of guessing where this is going, okay? So I'm going to put the x's together. X squared minus 2x plus y squared equals to 0. And what are you tempted to do here? No, not run away and close your computer. You're tempted to complete the square, right? So this is the same as x squared minus 2x plus 1 minus 1, right? Which is x minus 1 squared minus 1 plus y squared equals to 0. You can complete the square any way you want. But in the end, you're going to get x minus 1 squared plus y squared equals to 1. What is that? Well, we know it's a circle, radius 1, and its center is 1, 0. And if you look at the picture we got, I mean, I sort of deliberately drew it less than a circle, right? Because I didn't know, but it turns out it is just a circle, right? That's exactly it. Boom. That good? I've lost somebody. Shouldn't have made that joke. It's good. All right. Good. Okay, so one last example and I'm done. It's extremely similar to this one, but we're not going to be able to transform to rectangular coordinates. The equation in rectangular coordinates is quite complicated. So it's a more natural curve in polar coordinates. Okay. Oh, I should add something before though. So let's just notice. Yeah. So I've got r equals 2 cos theta gives me this circle. Now you have to be careful because the way that when theta goes from 0 to 2 pi, we actually go through the curve twice. You have to be careful with this. One way to avoid this, if we take minus pi over 2 less or equal to theta less or equal to pi over 2, right? If you start at theta equals minus pi over 2 at the bottom, and you go up like that, you'll go through the whole curve just once, okay? So we go through. This will be important later on. Okay. But that's not what I wanted to, well, that's one of the things I wanted to say. But the other thing I want to say is consider the following. The set of all r theta such that theta is between minus pi over 2 and pi over 2, and r is between 0 and 2 cos theta. What is that? Okay, that looks a bit complicated, but it's not. Okay, so, and this is sort of the typical kind of thing that we'll see in our next class, where you have a region over which you want to integrate, and you will describe it in polar coordinates as a type 1 polar region, which is exactly what we have here. Okay, and the key point is to find the curve, which we found, which is r equals to 2 cos theta. So look at this part here. What does it mean that r is between 0 and 2 cos theta? It means if you fix an angle, right, if you choose some angle theta, the possible values of r are anything between 0 and 2 cos theta. So it starts here at 0, and it goes right up to the curve. Right? And you take this for any segment, it's all possible points like that, right up to the curve. So if you're going from minus pi over 2 to pi over 2, what do you get? That's the inside. It's the disk, right? You're going to get every single point inside here, okay? So that's the way you can describe this off-center or off-origin disk, okay, in a sort of not too complicated way to some extent, okay? Right? So again, you fix an angle between minus pi over 2 and pi over 2. For a fixed angle, r can be anything from 0 up to the curve. So it's exactly the inside of the disk. Okay, that was not my last example, sorry. Okay. You know what? So here's what I'm going to do. I'm going to stop here, and I'm going to do the last example on Wednesday before the quiz, and maybe a little bit more, but that will be it. And then on Thursday, I'll finish the material. Okay, so I'm going to stop here for now. And but basically, we've seen almost everything we needed to see in polar coordinates. So just one last example that I'll do next time. Okay. Are there questions or comments? Have a great day too. All right. Excellent. Okay. So I'll see you Wednesday. Bye.